In this lecture, we're going to talk about equivalence formulas, sometimes known as equivalence factors. In particular, we're going to cover the following. First, we're going to talk about the purpose for equivalence formulas. And then we're going to cover 4 classic equivalence models or formulas. We will talk about the single cash flow, the uniform cash flow series, the arithmetic gradient cash flow series, and the geometric gradient cash flow series. Let's talk about the purpose first. Purpose is very straightforward: to facilitate performing equivalence calculations. That's it. The purpose of equivalence formulas is to help simplify our equivalence calculations. Now, it won't do so in every case, but there are many kinds of common scenarios wherein we can use these equivalence formulas to help do our equivalence calculations. Now, I would guess about halfway through this lecture, you're going to begin to wonder whether or not this is really simplifying things or not. In this lecture, we're going to show you the development and use of these equivalence formulas. You have not yet had much opportunity to use them in, say, your homework. I think you'll find once we get through the development and use of these equivalence formulas or equivalence factors, that you'll be able to see fairly quickly they do simplify our calculations. But that is the purpose, to simplify our equivalence calculations. Now, these particular models are based on a cash flow convention. That is, there are certain situations where we can envision certain kinds of stylized cash flow patterns occurring into the future, and that we can develop some formulas to simplify our calculations, our equivalence calculations, in dealing with those kinds of cash flows. And we call this a cash flow convention. There are different kinds of cash flow conventions, and in fact, your textbook discusses them. In this class and in these lectures, we're going to focus on one model in particular. It's probably the most popular model in practice, and that is the end-of-period cash flow model. Specifically, what this model assumes is that cash flow, represented by the arrows here, will occur in discrete amounts at the end of increments of time. Now, those increments of time could be the year, which has been the increment of time we've used by and large up to now, but it could be a quarter year, a month, a week, a day. It could be any increment of time you so choose. The notion behind the end-of-period model is this. We assume that if we forecasted, say, a receipt of $10,000 during the course of, say, the next year, that we will assume that that $10,000 will occur as a discrete amount at the very end of that period of time. Now, there are situations where that may be a very exact approximation, no approximation at all. There may be situations where our expectation is we will receive a discrete sum of money, $10,000, at the end of that period of time. Most practical problems, that's not the case. More often than not, when we're forecasting, say, the revenue that we might receive on the sale of a new product, what we may forecast is that it's our expectation that during the course of the next year, each and every day we'll be selling this product. And it is our expectation that by the end of the first year, in total, we will have received net revenue of $10,000. Now, that revenue has been coming in day by day, each day, for 365 days a year. Our ability to forecast that level of detail, though, may be very, very difficult. And so what we do is an approximation. We just assume and treat the $10,000 occurring as a discrete amount at the end of the first year. Rarely does this level of approximation have a significant impact on the ultimate decision that you will reach in performing an engineering economy study. It's basically a trade-off. We're trading off the level of detail that one wants to deal with in doing an engineering economy study to facilitate the calculations of actually reaching a decision. But that's what the end-of-period cash flow model assumes. It assumes cash is occurring in discrete amounts at the end of each period of time. Many engineering economy studies, the basis of time used is the year. And because it is used so frequently, often you'll hear this model referred to as the end of year convention. It's nothing more than a special case of the end of period model, where the period of time they happen to have selected is the year. But again, the increments of time can be any increment that you'd like to choose. We're going to cover 4 classic equivalence models. These are not the only ones. There are many more than just these 4. But if you can understand the development and use of these 4 models, you'll be able to understand the development and use of any other equivalence model that you might encounter. 2 of these, by the way, you've already seen. We just didn't tell you that when we introduced them. We're going to talk about the single cash flow model, which you've seen, the uniform series, which you've also seen. But then we're going to talk about the arithmetic gradient series and the geometric gradient cash flow series. What we're going to do now is basically develop a formal model, a representation to be able to do equivalence calculations when one is faced with different kinds of classic cash flow patterns. One is the single cash flow. That is, we may have an opportunity to receive some funds P at some point in time T sub 0. And we would like to know what future amount F at time T sub n is equivalent to that sum P at time T sub 0. We've already seen numerical examples of this. We're just now formalizing this in a more specific, general kind of representation. T sub 0 here, time T sub 0, can be just about any point in time. It's not necessarily today. It could be some point in time in the past. It could be today, the present, or it could be some point in time out in the future. In other words, this is a relative time scale. Time T sub n is simply n periods after time T sub 0. So what this time scale is expressing is basically the difference in time between the occurrence of P and the occurrence of F. They're n periods apart. What we'd like to do is to have a means to be able to calculate this equivalence, and we can do that using our standard formula that we've already developed. That is, the future amount F is equal to the present sum P times the quantity 1 plus the interest rate in which I can invest cash flows, raised to the power T sub n minus T0, or, simplifying somewhat, it's P times the quantity 1 plus I raised to the power n. Now, notice, this quantity, 1 plus I raised to the power n, just that factor, not the P, is a function of 2 items, the interest rate and the number of compounding periods n. If I wanted to, I could calculate various values of that factor by substituting in values of I and various values of n, and I could tabulate that in the back of your textbook such that if I wanted to perform this equivalence calculation, I would not necessarily have to go to this formula. I could look it up in a table in the back of your book, and that's exactly what your author has done. And we will represent this formula, this factor, the quantity 1 plus I raised to the power n, with this equivalence factor, this mnemonic representation, which is read, find F given P when you can invest funds at interest rate I and they are compounded in periods, and those are tabulated in the back of your book. For example, what future amount F at time 8 is equivalent to $100 at time 3 if you could invest funds at 5% per year? What we're asking is, I need to find the equivalent amount F for this $100 compounded forward 5 periods, because the difference in time between the occurrence of F and the $100 is 5 periods. Using my equivalence formula, I can write that this way. F is equal to $100, the present sum, times the equivalence factor. Find F given P when you can invest funds at 5% per year, over a 5-year compounding period. I can look up the value of this equivalence factor in the back of the book, and if I do, I will find that to be 1.276. Doing the multiplication, I end up with $127.60. In other words, the concept of equivalence, you would be indifferent between receiving $127.60 in the 8-year or $100 at time 3, provided you could invest at 5% per year. Now, there may be situations where I'm given F and would like to find P. So obviously, all I have to do now is just take the reciprocal of what I just did on the preceding slides. In particular, I write the equation as the present sum P at time t sub 0 is equal to the future sum F at time t sub n times the quantity 1 plus I raised to the power t sub 0 minus t sub n. Simplifying the formula, it becomes F times the quantity 1 plus I raised to the power minus n. That is, I'm finding an amount. I'm discounting F back in periods. Again, you will notice this factor here, this quantity, 1 plus I raised to the power n, is a function of two items, the interest rate and the number of compounding periods. I could substitute in various values of I and n, do the calculations, and tabulate that in the back of your book. And I can represent that through this equivalence factor, find P given F when you can invest at interest rate I for n periods. For example, what present sum P at time minus 3, it is 3 periods in the past, is equivalent to $500 7 periods into the future if I could invest at 6% per year? Writing my equivalence calculation this way, it is P is equal to that future sum, $500, times the equivalence factor, find P given F when I can invest at 6% per year, and discounting it back 10 periods. That is, there are 10 periods between the occurrence of F at time 7 and the equivalent sum P that I'm searching for, which is going to occur at time minus 3. Doing this calculation and looking up that factor in the back of your book, you find it to be 0.5584, which results in $279.20. In other words, you would be indifferent between the receipt of $279.20 3 periods ago or $500 7 periods into the future if you could invest at 6% per year. Let's take another equivalence model. This one you've also seen in other numerical examples. We're just generalizing it now. This is the uniform cash flow stream in which we envision the receipt or expenditure of a stream of cash flows represented by an amount A. That is, you would receive amount or spend A each period for the next n periods. Bear in mind we're using the end of period cash flow convention, which means the first cash flow occurs at the end of the first period of time. Notice there is not a sum here at time sub 0. We're using end of period, so we're assuming the cash that is received here occurs as a discrete sum at the end of that first period. So the first cash flow occurs at time t sub 1, and we receive those cash flows each and every period as a uniform stream for n periods until time t sub n. Well, there'll be lots of situations when we may want to find, say, an equivalent future sum, F. And we would like to be able to have a convenient means to find F. Well, we now know we could calculate that quantity F simply by taking each of the individual cash flows and compounding them forward at interest rate I and adding them all up as of time t sub n, and we would know what that future sum F would be. And we could write the expression this way. That is, F is equal to the first cash flow A compounded forward n minus 1 periods. That is, we're going to go from time t sub 1 to time t sub n, plus the cash flow at the second period of time compounded forward n minus 2 periods, so on, so on, so on, until finally we add in the last cash flow, A, which already occurs at time t sub n. Turns out there's a much easier way, a much more concise representation for this formula and this calculation. What I'm about to do is show you how we can in fact reduce this equation down to something that's a lot more simple and straightforward. What I'm about to do is basically algebra. That is, the concepts of equivalence come to here. From this point on, we're talking algebra. I'm just going to do a mathematical manipulation of that equation to see if I can reduce it down to something far more simple. The first thing I'm going to do is I'm going to factor out of this equation A, the amount A, which is common to all of those terms, leaving this expression. Then I'm going to do something a little bit different. Then I'm going to multiply this expression by the quantity unity, 1. But it's going to take on a rather interesting expression. It will look like this. It will be the quantity 1 plus I minus 1 divided by 1 plus I minus 1. Now, I've not changed this equation mathematically in any way. What I'm going to do is take the denominator and move it over to the left-hand side. And then I'm going to take the numerator and I'm going to multiply it through everything on the right-hand side. And if you do that, the expression you will get will look like the following. As you look at this expression here at the bottom of the screen, and you look at the right-hand side, you will notice something rather interesting. Most of those terms cancel out. In fact, all that is left is the first term and the last term. And over here on the left-hand side, the quantity 1 plus I minus 1 is really nothing more than just the interest rate I. So, let me rearrange the formula. Let me move the interest rate I on the left-hand side over to the right-hand side, and if I do that, you'll end up with this expression. A times the quantity 1 plus I to the n minus 1, that whole quantity divided by the interest rate I. So now, if I wanted to find some future sum F that's equivalent to a uniform stream of cash flows A that occur from time t sub 1 to time t sub n, I can solve this equation. Notice that this expression, that is the quantity in the brackets here, is a function of two items, the interest rate and the number of compounding periods. So again, I could solve that expression for different values of the interest rate and different values of the number of compounding periods and tabulate that in the back of your book. This expression here, this formula, can be represented by this equivalence factor, which is read, find F given A when you can invest funds at rate I for n periods. As I'm sure you can appreciate, there's going to be times when I am given F and I may want to solve for A. Well, to do that, I simply rearrange this particular equation to look like this. And I can represent that through an equivalence factor, which is read, find A given F at interest rate I for n periods. Take an example. What future amount F in 4 years is equivalent to $50 each year for the next 4 years if you could invest funds at 10% per year? Writing my equivalence factor, it is, to find F, it's the annual sum of $50 each year times the equivalence factor, find F, given A, which is 50. When I can invest at 10% per year for 4 periods, I can look up the value of this factor in the table in the back of the book. I will find that value to be 4.641. Doing the multiplication, I find that F becomes 232.05. In other words, you would be indifferent in a choice between $232.05 in 4 years or $50 each year for